So, 5G Technology World, we are at DesignCon 2020 in Santa Clara. Mike Schecker from Rohde Schwarz is going to tell us about jitter separation on an oscilloscope. Now, why do we care about jitter separation, or what is even jitter? Well, if you've got a stream of bits coming along down your channel, guess what? They don't all arrive at exactly the same time. There's a little bit of difference from one bit to the next, or from one group of bits to the next, and we need to know why that happens. And so there are many different reasons for different forms of jitter, but why does that happen? Mike's going to tell us why. How do you find those different forms of jitter?
Thanks a lot. So here, we're at DesignCon. I wanted to talk a little bit about jitter. So first of all, think about jitter. Jitter is all about bit error rate. The idea behind it is when those edges transition at the wrong time, then a receiver, digital receiver, can mistake a 1 for a 0 or a 0 for a 1, and then you have corrupted data and doesn't get to the other end.
Doesn't work.
So we care a lot about jitter because it is one of the main causes of bit errors in the system. And if you think about jitter, it's caused by two primary factors. One is what I like to refer to as waveform distortion. So as the waveform passes down a non-ideal channel, cable, interconnect, or a backplane, or even a trace on a PC board, it's going to distort the waveform. And that distortion results in errors in the edge positioning, and they're sort of dependent upon the bit pattern. So depending upon the bits that went before it, it's going to excite that channel differently and cause different delays through it. And so that's the one source of error of jitter that is most common, most problematic, and also the one that is the most easy, and it's in a lot of ways easiest to fix, because that just makes you changing the channel. Another form of jitter is called random jitter. Random jitter is usually noise related. Not a whole lot you can do about it. Typically just build low noise oscillators and that takes care of it. So what we've done is we've designed a jitter measurement software that allows one to understand those waveform related jitter sources and understand better where they're coming from. So traditional jitter measurements on an oscilloscope, you acquire a long waveform of data and you basically measure the crossing times of the data waveform. And in those measurements of the crossing times, you compare that to the ideal crossing time and you collect an ensemble of timing measurements. From there you figure out, okay, I could do some statistical modeling and figure out what part of it's random, because that tends to look Gaussian, what part is not random, that tends to look different from Gaussian. That's been the tradition for many years. What we did is we sort of took a fresh look at jitter and we said, well, what's the real cause? And it turns out, of course, it's the channel. So rather than measuring just the timing points, we take the entire waveform and we build a signal model on that waveform. The model consists of several major parameters. Number one is the step response of the channel. The step response tells us all those data-dependent jitter and where they come from, and they give us insight into how to maybe repair them as well. Another form of jitter is something called periodic jitter, which is usually sinusoidal or repetitive movement of the edge in timing and also in amplitude. So what we do is we model, based on the data that we capture, the entire data record, we model the periodic components, both vertical and horizontal, and we model the step response. And then from there we get waveforms for each specific jitter type. We have a DDJ waveform, we have a PJ waveform vertical, and a PJ waveform horizontal, and then we have an RJ waveform. All those four waveforms make up our model. And so then what we can do is we can break down the total jitter by adding up those waveforms and essentially measuring the jitter on that modeled waveform. So we're no longer looking at the data from the scope, we're looking at the model, and now that we have a model, I can measure the jitter for any time I want, as large a set as I want, because I've got the entire waveform model. And that's what this bathtub curve shows you. It's essentially the jitter versus sample size. Sample size can be seen vertically. We express it in terms of bit error rate. 10 to the minus 12 is the standard, which means a trillion bit interval would have this much eye opening from here to here. That's the opening of the eye in horizontal dimension. This is a new result. This is the step response we get from the channel during the modeling process. The cool thing about this is it gives us insight into where the data-dependent jitter is coming from. So you can see this rounded edge, typical when you have a limited bandwidth and the channel is not full bandwidth. If you look over here on the right, you can see an ISI. That is the data-dependent jitter, and you see it's coming out about 15 picoseconds. That's how much variation in the timing I'm getting based on just this channel response.
An ISI, that's intersymbol interference.
Intersymbol interference, that's what you were referring to initially, where you're talking about the symbols arriving at different times. That is the degree of arrival time disparity. Now we have all the other standard jitter numbers like RJ, for example, and that's the random part of the jitter. But I want to focus on this right now because what we're going to do is I'm going to change. Right now I have a waveform connected to channel 3 of the scope that's going through a long cable, and that's the thing that's limiting the bandwidth. What I'm going to do is I'm going to switch to this channel, which is a short cable, which ought to support a higher bandwidth.
Okay, so you got a very short cable here. Just,
maybe 6 inches, 7 inches
yep.
long. Yep.
And this one is...
that's almost 2 meters long.
It's a
wrapped
lot longer.
up, it's pretty long.
Yep, okay.
So when I switch, I'm going to go over here and I'm going to switch the input to channel 1, which is the short cable. And it's going to compute, and it's crunching through the numbers here. Now one of the other interesting things about our jitter software is because we're using a signal model to do the measurement, if you look at the record length size, it's only 1.6 megasamples. Now if you know jitter measurements, typically you want 20, 50, 100 megasamples to do it.
Right.
But because we're using the whole waveform, we don't need that much data to do it, to get the jitter measurement. And so it's a much more efficient process than currently exists. So once it's finished computing, this should change. And you can see now it's a much sharper rise time because the channel's got a higher bandwidth. You can also see that the ISI is now reduced to 6.3 picoseconds. Now, what's really interesting is this step response is 20 nanoseconds long. That's a big chunk of time.
Yep.
That's about 100 bits of time. Now, current jitter measurement algorithms, what they do to measure data-dependent jitter is they send a repeating pattern down the line. And every time a pattern repeats, you look at that bit and you measure it and you average it to figure out what the data-dependent jitter is. And you need that repeating pattern to do it. Because we're doing a signal model, we don't need a repeating pattern. We can do this measurement on random data. And in fact, right now what we're doing this measurement on is what's called a PRBS 31. And that's a pattern that repeats every 2 billion bits. It's a very long pattern.
It is.
There's no way to capture
the 31st power of bits.
That's a lot of bits.
That's a lot of bits.
You normally cannot, well, you can't capture that in any memory, right?
Right.
And we don't need to capture it. And so we're actually measuring on the PRBS 31. I want to try something different. So if I had a shorter repeating pattern, I wouldn't be able to measure this 20 nanoseconds. I'd have to measure a smaller chunk. And if I do that, now remember this number, 6.3 picoseconds.
Okay.
We'll come back to that. So I'm going to switch. Right now I'm looking at 100 bits. I'm going to switch to 7 bits, which is kind of a typical short repeating pattern like a PRBS 7. And you can see the number changes. Now my ISI is only 2.7 picoseconds. Why? I don't have the entire response anymore. So there's detail out here that's off screen that we can't capture because we didn't capture enough.
You capture enough bits. That's why you're not seeing the sharper edge here, and there was actually a little bit of a spike, but you're not seeing it because it's almost like not having enough samples.
Exactly. Exactly.
You're missing some of the data in between.
That's true, and that's I think one of the benefits of this method here is we get the very complete picture of what's going on in the system, and even relatively short channels do require fairly long step responses to see the total effect. And the other cool thing is, now that I have this step response, and if I have an ISI problem, I can usually see it in there as a discontinuity. Oh, I must have a impedance mismatch or a bad solder joint, and we can even get technically into the chip ball grid array because I'm actually just measuring the signal coming out, and it gives me all the information going all the way back into the chip die. And so if I have a packaging problem, I would probably see it in there as well. In that measurement. So this is kind of a new approach, but we think it's pretty exciting. We think it's pretty powerful, and it gives a lot of insight.
Very good. Mike, thank you for your time. Appreciate it, and good to see you again.
Great to see you. Thanks a lot.